we will introduce spherical coordinates and how we integrate, how do we do triple integrals using spherical coordinates. So these are different coordinates than polar coordinates or spherical coordinates, rather. These are spherical coordinates which are different than polar coordinates and cylindrical coordinates. So the way so these are the x, y, and z axis. And if we have a point up here, which comes from this projection on the xy plane, the distance from the origin to the point is going to be labeled as rho. So this is going to be rho. We're going to introduce a new lowercase Greek letter, which is going to be phi. In many books, they write it like that, same thing. But most people who handwrite it write it this way. So they're the same thing. And this is the lower case Greek. I call it phi. A lot of people call it phi. I don't think it makes much of a difference. So phi. So that is phi or phi, whichever way you want to call it. And rho, you are familiar with the rho. Unfortunately, we're using the same letter as the one we use for density. It's just the way it is. So when you see rho, you gotta be aware that it could be the distance from the center to a point on spherical coordinates, or it could be the density, but that's a different kind of meaning. Theta is also going to be involved. Theta is the normal distance from the x-axis to the projection, to the projection of the point on the xy axis. So theta is that. R is here in cylindrical coordinates. And then the new letter we're using is the angle, I call it the drop angle from the positive z-axis down to the line or the segment that connects the origin with the point, and that is going to be labeled phi. So theta can go all the way around. Theta could go from 0 to 2 pi, and phi goes from 0 to only pi, because you don't want phi to swing all the way down and past the bottom of the z's. If you want to do that, just change the theta, and that should do the job. So be aware that phi goes down in any direction that goes down from the positive z-axis, but it can go in any direction that you want it to go using theta. Yep. All right. Now, this R is not used directly for the R that is here. It's not used directly for spherical coordinates. And you can actually see the Z is this distance. That's Z. Yep. So we do know that R equals X. X is equal to R cosine theta. Y equals R sine theta. And of course, Z equals Z. That's in cylindrical coordinates. Okay. In spherical coordinates, if we observe, there is rho, there is a 90-degree angle here. So we got a right triangle going on here with a point, the origin, and the projection of the point down to the XY plane. So the Z, looking at this triangle, is, phi is here. Phi will be again there. So that is where phi is in this triangle. And based on that, since we have a right triangle and this is rho, then Z is rho times the cosine of phi. So z equals rho cosine phi. Um, x would be this distance, which is r cosine of theta, but r, just like we found z to be rho cosine of phi, well, r is the opposite side to this angle in this triangle. So r would be rho sine of phi, rho sine of phi. That's r. And consequently, x is that rho sine phi cosine theta. So that gets to be more than before. And y would be r, same r, rho sine phi, but now sine theta, because y is r sine theta, but in turn r is rho sine phi. So that's why we have rho sine phi and rho sine phi for x and y, and we have rho cosine phi and nothing else that involves theta. So these are the conversion equations. By the way, it is handy to know that x squared plus y squared plus z squared, whoops, equals rho squared. Just as up here, x squared plus y squared equals r squared. But r is not really involved in spherical coordinates. I'm just using that as an auxiliary drawing so that we can go from x, y, z into rho theta phi. Yep. So there we have it. Any triple integral, a 1, 2, 3 over some solid of f of x, y, z with respect to its volume, the volume of the solid, is equal to the triple integral of the function. See, but instead, everywhere where you see an x in the original function, we're going to replace it with this big long thing. So we're going to have rho sine phi cosine theta, comma, the y, rho sine phi sine theta, and then rho cosine phi, close parenthesis. I'm running out of space there, so we got to multiply. I'm going to put a dot. This is not a dot product. This is just multiplication, the regular multiplication. And we got to multiply by something. I'm going to put a box. And then we're going to have d rho d theta d phi, an iterated integral. So what we have to have here is the Jacobian. The Jacobian in polar coordinates and cylindrical coordinates was r. This time, it would be a little naive to think that the Jacobian is going to be rho. By the way, the limits of integration here are to be determined, and so are those to be determined. I'm writing a general formula, so that's why I'm not determining them. But once we start working on a problem, we have to determine the limits of integration of the new integral. Okay, so we are missing the Jacobian. Let's check how the Jacobian may look like. So if we have a delta rho, so that's like a delta that represents a delta rho, and a delta phi. All right, I'm going to use some projective geometry to make a nicer there, because this is coming off of a center. And then we have a delta theta, again using a little bit of geometric projective geometry. And then this goes this way. and then it comes down to a point here. So we have a wedge. I'm thinking of a pumpkin. If you cut a square on the pumpkin, when you pull out the piece that you cut off, it's not a square. Well, it may look squarish on the outside, but the outside of the pumpkin is going to be round, and so is the inside. And then you got this going in, this kind of wedge going in. So this is what we obtain when we have delta rho, where the distance from the center of the origin goes out, and then we have a delta phi coming down this way, delta phi. So that is the angle that changes, and a delta theta. I'm going to put it there, delta theta. So a little change on the data, and on the theta goes across horizontally, delta phi goes down. This is a three-dimensional wedge, and then delta rho this way. So we want to figure out how this volume compares to x, delta y, delta z kind of volume. You know, when we are in Cartesian coordinates, you got delta x, delta y. So you got a nice cube, and then delta z. So you got nice square cubes, boxes, and so you got your delta y and delta x, and up here delta z. So the volume is precisely delta x, delta y, delta z, and that's why we don't need to multiply by anything extra, because just the differentials, the deltas, do the job for figuring out the volume. Here we have to do something to accommodate this curvature, and this is far away from the origin, and the farther away we are, if we keep the angle the same, the bigger the wedge will be. So this side, assuming that rho goes all the way out to here, this side, as you know from trigonometry, is the radius. This is an arc length, so that is the radius times the angle. If we assume the angle is delta phi, then this is rho delta phi. And you may think, well, so that side should be rho delta theta. It's not rho delta theta. So I'm going to put rho delta theta a little far away, and I'm going to cross it, because we're thinking, well, this is going down, so the arc is just rho delta phi. So if you go this way and we sweep the angle theta across, isn't it going to be the same, rho delta theta? And the answer is no. And I'm going to show you a picture of why not. So pretend you are on a big sphere like the Earth, and you got meridians going down this way. So those are maximum circles. That gives us the longitude. And if you, so all of those big circles, this goes in the back also. All those maximum circles cross at the North Pole and the South Pole. And if you cover any kind of an angle on the equator between those two from the center, well, if you go the same angle up here, you're going to get a much smaller distance. And in between, you're going to get a bigger distance than that up here, but smaller distance than down here. So we have to take into account how far we are from the equator, or how far we are from the North Pole or the South Pole, to determine this arc. This arc is not a maximum arc. I guess that's where this is coming from. This is not a maximum arc. The phi does give us a maximum arc because it just goes straight on down. But when we sweep theta sideways, we have to take into account that this is already up a certain distance from the equator. And so that causes this arc to be smaller. I guess the answer would be phi, rather rho delta theta if we were on the equator. Sure, no problem. But if we are off the equator, then we have to account for that. And we know, so this circle up here, let's talk about this circle up here. So this arc is a part of this circle, and this circle has a smaller radius than the radius of the original sphere. What is the radius of that? Well, let's draw a circle now. So pretend we are here at this point, so that represents this point. And we want to know, and this is the vertical, and we want to know this radius around, because that would be the radius of this circle up here. Well, we're assuming this is phi, because phi is the drop. And remember, this is rho. So this radius, so this distance, which would be the radius of that circle, is it's opposite to phi, and we have a right triangle here. So that would be rho sine of phi. So the reason why we multiply by rho is because going down, we do have the same radius of the circle. So whether you're here or here or here, that is still the same distance. We're using this arc, this big circle. But once you are up there, then we have to use a different circle. And the radius of that circle, so the radius is rho sine phi. Okay, so this length is actually rho sine phi delta theta, not that. Okay, so rho sine phi delta theta. And that the reason for that is because of the way this looks on a big sphere. Okay, so the volume of this wedge is approximately, especially when the quantities are small. So when the angles are big, we're going to get big chunks of pumpkins, for instance, just big things. But when you cut a very, very tiny square of the pumpkin and you pull it out, that should look very much like a cube or like a box. So the volume is about length times height times depth, approximating this as if it was a box. Of course, it is not a box. But when the angles are very, very small, okay, so when the angles are very small, this line will be very parallel to that. That doesn't make sense. Lines are either parallel or not parallel. But what I hope you know what I mean. What I mean is they're close to being parallel if this angle is very small, and when this angle is very small, also those two lines seem to be parallel, and consequently we have close to a box when quantities are small. And we're going to take little bits to form the integral. So the box would have volume of delta rho times rho delta phi times this weird one, but the reason why is because we got to take into account that this arc is taking an angle above the equator. Now, if we're on the equator, phi would be 90 degrees because it is the drop from the North Pole. So phi does not measure the latitude, it measures from the North Pole the angle down. So if that was 90 degrees, then sine of 90 degrees is 1, and we do end up with the correct arc. If phi was 0, then there would be no arc. We would be right on the North Pole, and consequently, we do get 0. Anyway, so this is rho, rho sine phi delta theta. This is a multiplication. We're going to put all the deltas on the right. So this is equal to, there's one row, two rows, rho squared, and one sine of phi, sine phi. And then we can multiply by delta rho, delta theta, delta phi. Okay. So if we want to use those deltas as opposed to using those deltas? Yes, we can, but we have to include this extra factor in the picture. Otherwise, our multiplication, our volumes are going to be off. They're not only going to be off, they're going to be off inconsistently, because at some points the one will have one angle or another angle, or one distance or another distance. So if we had a constant, then that is no problem. We just use proportions. But no. This is missing. This is a huge big deal. So this is the Jacobian, what we need to include to be able to use those as differentials. So we put that here, rho squared sine phi. I just want to check. Yeah, for a moment I thought I was just talking without recording, and that scared me, because then I would have to do all of this all over again. So back to this. If we want to go from x, y, z coordinates into spherical coordinates, we have to exchange every x with that, every y with that, every z with that. In addition to that, we have to multiply with the Jacobian, and then we are set. Sometimes, even though it seems that we are adding a lot of things into this, it is worth it, because in some cases we will have a very, very nice box. So a spherical box, this is what I call a spherical box. This is not this is a box, a regular box. This is what I call a spherical box, because we can, if you go from, say, from 1 to 2, and then from certain angle to a certain angle and on the phis, and certain angle to certain angle on the theta, we get this kind of picture. So if we were integrating, all of the limits of integration would be constants. So that's what I would call this kind of shape, would be spherical box. Remember, we had rectangles, polar rectangles, which don't look like rectangles. Same thing here. So just to remind you, a polar rectangle, a generic polar rectangle, looks like it's a plane. That's a polar rectangle, because then the angle is just fixed. This has to be straight there. And this is the polar rectangle. And these curves are just sectors of circles, concentric circles with the same center. So this is what I would call a polar rectangle. Likewise, this wedge is a spherical box, not a rectangle, because this is a three-dimensional. Let's do an example. I think we're just going to do one example. I guess we can call it one. So we want to find a triple integral of z over a solid with respect to the volume. And we're going to have a cone where the bottom of the cone is on the origin, and on top of that we're going to have a circle, not a circle, rather a sphere, and the radius of the sphere will be the square root of 2. So the cone, so we're going to, E is a solid with cone in bottom, and sphere on top. The other way to say it, inside the cone and inside of the sphere. So the intersection between the cone and the sphere. The cone, the equation of the cone is square root of x squared plus y squared. So that is the cone. And the equation of the sphere will be x squared plus y squared plus z squared equals 2, not 1. So we don't have a unit sphere. We have a sphere whose radius is square root of 2, of course. The reason for that is because I wanted a solid so that if we project down to the xy plane, we do end up with a unit circle. So this on the bottom is a unit circle. However, the sphere, which is out here, will not be a unit sphere. The radius of this sphere will be square root of 2. So it's a bigger sphere. What happens is that when the cone goes through the sphere, it is going to cut in such a way that this distance, the radius of the projection of this cone after it is being cut by the sphere will be 1. And so this solid is not flat on top. I think of it as an ice cream cone. It has a curvature here. I'm exaggerating a little bit. The curvature is probably a little more flat, not as curved. And then we have the ice cream cone. So we want to integrate this. By the way, in the very, very previous video, we did this example, except that we have a flat top without these. So let's do this. All right. So the setup, triple integral z with respect to the volume over E. If we set it up with x, y, z coordinates, then okay, z would go from the cone. So we're going to integrate z with respect to z, and that was given here. That's part of the problem. That could have been x or y or something else, x plus y or xy. Typically, we put things that are reasonable, and that's reasonable. Otherwise, things get out of control. So z is going to go from the bottom, which is the cone, this z, square root of x squared plus y squared, to the top, which would be this z, square root of 2 minus x squared, whoops, minus y squared. That's bothering me, so I'm just going to erase it. Anyway, minus y squared. All right. And then if we project the cone down to the floor, the radius of the floor is going to be 1. This is a square root of 2 length. But when we project down, we're going to end up with 1, which makes sense because 1 plus 1, this is a 45-degree angle. So 1 squared plus 1 squared equals 2. And by Pythagoras, it makes sense that this is the square root of 2. Yep. And when we write down the equation of the sphere with radius of square root of 2, we square the radius. So that's where that 2 come from. Okay. The y, once we project, we're going to get a unit circle on the floor, and the unit circle goes from 1 minus x squared to 1 minus x squared, root negative and root positive there. The reason, again, is because the radius down here is 1, even though this distance is square root of 2. Watch out. And then we go from -1 to 1. Okay, we're going to do this, I think, 3 times. Let's do A. So A is going to be example 1A. Let's do it as is. Okay, so -1 to 1. And I don't think it's going to take us longer than this page. But let's see. Integral from negative square root of 1 minus x squared, positive 1 minus x squared. Now remember, this is going to be z squared over 2 when we integrate with respect to z. So we're going to have a half. And again, z squared over 2, there's the over 2 part. Z squared, so we're going to square that. 2 minus x squared minus y squared. And then we're going to square this. So again, minus x squared minus y squared. Back here, I missed the dx. dy dx. So that takes care of this z. If you pay close attention, you see a negative x squared, another negative x squared, so that makes 2. Negative y squared, that makes 2 of them. So we got a double 1, double x squared, double y squared, but we are multiplying by 1/2. So this is really -1, 1, negative square root of 1 minus x squared to positive 1 minus x squared. And so the 2's and the half cancel out. So we simply end up with 1 minus x squared minus y squared dy dx. Now, this looks very, very familiar. In the video 52401, there it is. We did the cone without the ice cream, without the top. And we ended up with this integral from -1 to 1, negative square root of 1 minus x squared to positive 1 minus square root of 1 minus x squared. And we have the 1 minus x squared minus y squared, just like this. The difference is that here we do have the 1/2, there we don't. 1/2, not 1/2. The answer back here was pi over 4. So since this doesn't have a half, I'm going to piggyback on example 2 of the video 52401. And what was the answer? Pi over 4. But that one did have a half. This one doesn't. So we're going to double this, and that's going to give us pi over 2. So you can do the math if you want to, but we already did it. So pi over 2. Ta-da, there's the answer. Okay. That's the answer for this. We did not use spherical coordinates, but if you remember, when we did this in the video 52401, we went from here to here, and then this one was straightforward. It took us a page to find this value, and it took us another page to find this value. So there's 2 pages going on of work going on here. So when I jump to here, we're actually skipping about 2 pages of work. All right. Can we do this with cylindrical coordinates? I'm going to do this on a new page. So B using cylindrical coordinates. Okay. So in cylindrical coordinates, remember, x squared plus y squared is r squared. Take square root of that, and we end up with r. Here we have 2 minus r squared. So using cylindrical coordinates, the triple integral of z with respect to the same volume with respect to volume over the same solid Okay, so z is going to go from r to the square root of 2 minus r squared. R square root of 2 minus r squared z dz. Yep. And then we have the unit circle. So we integrate with respect to r from 0 to 1, and with respect to theta from 0 to 2 pi. So this is the setup for cylindrical coordinates, which, by the way, was the topic of the previous video. But I just want to make sure we have more examples. So we go from 0 to 2 pi on the thetas, from 0 to 1 on the r's. We still have z squared over 2. So there's the over 2 part. Z squared, that means square that, 2 minus r squared minus r squared. So again, we have duplicity of r squareds, which cancels with this 2 in the denominator, and also with that 2 dr d theta. So 0 to pi, 0 to 1. So we just have 1. Oh, I missed something. Whoa. Stop everything. I cannot simply just change that without, because the delta r delta theta, if you just change delta r delta theta, you're going to get a curved surface. So we have to, it's not square. So we have to take that into account. Remember, we have to multiply by the Jacobian. Whoa, r. Whoops, I almost forgot it. I did forget here, but I remember before it was too late. So yes, Jacobian. Whoa. So that means there is an r in here that we need to multiply by r. Okay. And when we multiply, we end up with r minus r cubed. Remember that there's 2 divided by 2, that's the 1. Multiply with the r gives us r. And then we got 2r squareds divided by 2, we just get dr squared times another r cubed. Okay, now we're good. Dr d theta. So that's I'm gonna pull a fast one on you. This is r squared over 2 and r to the 4 over 4, but we're integrating from 0 to 1. So this is just from 0 to 2 pi, 1/2 minus 1/4, which is 1/4 d theta. We can factor that out. So again, 1/2 minus 1/4 is 1/4, 1/4. But then we multiply by 2 pi because the integral from 0 to 2 pi of 1 is, with respect to theta, is 2 pi. So the final answer is pi over 2, which is consistent with the answer we obtained back here in 1a. So this was as is, no trick, but even though this looks short, remember, this does not show 2 more pages of work. We got pi over 2 because we piggybacked on an example of the previous video. Here, this is the work, that's it. I did not add, there's no 2 hidden pages of work, that's it. There was nothing. So this already shortened our work by a lot. C, how about using spherical coordinates? Using spherical coordinates. All right. Let's see. We got the triple integral of z. Remember, that could be different depending on what the problem asks you to find. If it asks you for z, then you do z, but it could be x or x plus y or x squared y or who knows what. With respect to the volume, over the same solid. So using spherical coordinates, okay, remember the solid is this one. So we're going to integrate z, but z is rho cosine phi. So we're going to have rho cosine phi. Whoops. Whiteout takes too long. And my other, I hate to do this, but this is phi. I'm going to get another whiteout for this so that it looks a little neater. Anyway, so we're integrating over this ice cream cone. Okay, so rho goes from here all the way out to here in every direction. So rho goes from 0 not to 1. Mind, 1 is shorter than that because this is a diagonal. 1 is this, the shadow of the ice cream cone on the floor. That's 1. The diameter, the radius is 1. But this is longer. This takes into account the 1 plus more on a diagonal, and that is the square root of 2. So rho, if we integrate, I'm going to put d rho from 0 to the square root of 2. Very, very important. Phi is what I call the drop from the vertical to as far as it can go. And it's nice that when it drops this way, we have a nice, straight, smooth segment. All right. And how far does it drop? It only drops up to 45 degrees. And the reason is because of this guy has an angle of 1. So it drops only up to 45 degrees. Okay. So phi goes from 0 to 45 degrees. Of course, we're not going to put 45 degrees on our integral because we are in calculus. In calculus, we use radians. So that's pi over 4. And then theta, well, this ice cream cone is the same all the way around. We're not cutting a piece out of it. So theta is all the way around, which means that theta goes from 0 to 2 pi. Okay, so the first thing to notice is that those are nice numbers. They're solid numbers as opposed to back here. Those two are nice, but then this is variable. We deal with it relatively easily. So there was no too much drama to go from here to here, but there could be more drama. There's instances where had we had an X here, then things wouldn't be as simple. Anyway, but you know why I left this gap, don't you? What did I forget initially here? The Jacobian. Don't forget your Jacobian. Every time you're changing your deltas or your differentials, you have to have, for purposes of integration, you have to have a Jacobian. And the Jacobian is going to be rho squared sine of phi. Remember that came from this picture. You know, that wedge and that deal about the latitude. If we are in a different latitude, then we are in a different circle. So, okay. Theta is not involved in this picture whatsoever. I don't see theta here. There's no theta in those. So that means we're integrating from 0 to 2 pi. So all of this part, the two integrals in the inside can factor out. So we're just integrating from 0 to 2 pi d theta. So that's going to give us 2 pi. That integral was straightforward. The integral with the rho, again, this is handy. There's no variables. So we can just think the row, and we are multiplying. If we were adding, that's a different thing. If we're multiplying, then we can separate the integrals only, exclusively, when we are multiplying. And not separating, rather, when we cannot separate integrals is a major conceptual mistake. So don't do that. But here we have r cubed, and we are integrating with respect to, not r, rho cubed, and we are integrating with respect to rho. So rho cubed with respect to rho, I'm going to write it down actually. We're going to end up with rho to the 4 over 4 from 0 to the root of 2. And then we are integrating cosine sine. Well, that's handy because the derivative of sine is cosine, so we can easily use u substitution. So for the integral that involves the phi, which is this one from 0 to pi over 4, we can simply use u substitution. If this is u, then du is cosine of phi d phi, which is present there. So we're going to go and have u du, and so we have u squared over 2 from, of course, we're going to change the variable again, from 0, because we're using u, to 1 over the square root of 2. Okay. So that is 2 pi times square root of 2 to the 4. Well, square root of 2 times square root of 2 is 2. And then another 2 for another pair of square root of 2's. That makes a 4. So we end up with 4 over 4 for this portion. Let's put that in parentheses. And then here we have u squared. Well, that's 1 over square root of 2 squared is 1/2. Divided by 2 is 1 over 4. Okay, so that gives us 2 pi over 4, which is the same thing as pi over 2, which is consistent with the answer we obtained in 1a and consistent with the answer we obtained, rather, in 1b and consistent with the answer we obtained in 1a. So this example was done straightforwardly, just without any change of variables, using cylindrical coordinates. Don't forget your Jacobian. In cylindrical coordinates, r is the Jacobian. Using spherical coordinates, the Jacobian that we have to place is not as simple. The variables are not necessarily simpler, but oftentimes if the solid is the correct one, then we can have very, very nice limits. And that oftentimes make the integration simpler. Here, the limits, even though this wasn't too big of a drama to handle, it could have been. So the limits, having nice fixed limits of integrations can make things a lot easier. And I'm going to write a note about example 1. Oftentimes, I like to give my students problems where the cone, instead of having a nice 45-degree angle, is a different angle, like 3/4. So, or maybe an open cone. And I can easily achieve that by by having an equation that is the same, x squared plus y squared, and by simply changing the constant here, by putting a constant other than 1, I can easily change the angle. So let's say just put a, I don't know, a 5. Okay. So oftentimes I give students problems, similar problems to the one we just finished, but with a different cone. Now, this means that the slope of the wall of the cone is 5. It's a very, very narrow cone. You know, it looks even worse than this. I'm not making it as narrow as it should be, perhaps. Or is it? Let's see. 1. So if this is 1 unit, 1, 2, 3, 4. Well, so it's close to that. So then how do we go about changing the angle? So we don't have a nice pi over 4 angle as we did in the previous example. So the question is, if you change this into spherical coordinates, you got to deal with this angle. And how do I know the angle? Well, the tangent is invariably this is the tangent, the slope. That what I meant by that is the slope. The slope is the same as the tangent. I gotta make sure this is right. So this means that for every unit you go out this way, you go up 5. Yep. So this is 1. This is 5. The other way to think of it is this is 1, and this is 5. So what is this angle? Well, 1 over 5 would be the tangent of this angle down here, 1 over 5. So for purposes of converting this into spherical coordinates, there's other things going on, but only for purposes of the phi, the phi would go from 1 down to, rather from 0 to the arctangent of 1 over 5. Yes, if phi was representing this angle, then we would have arctangent of 5 over 1. But phi represents this angle, so we have the reciprocal, 1/5. Yeah, and then in some of the problems you have to deal with, you know, if I give this kind of situation, and sometimes the slope I give is not 5, is 3/4 or or 3/5, you know, some kind of fraction. Then you got to do the reciprocal of the fraction, and that's what goes in here. I'm not giving the whole story. There's more to this here, you know, more. But for purposes of what you're going to put in your upper limit for phi, that's what you want to do in this case, if we have this kind of cone. When you get down to the answer, you may end up with expressions that involve the sine of the arctangent of 1 over 5, but this is a precalculus problem. Let me just remind you how we go about it. So opposite over adjacent. So pretend you got an angle, 1, 5. You find the hypotenuse by Pythagoras. This is the angle in question, corresponding to the arctangent of 1 over 5. And of course, the hypotenuse is going to be square root of 26 because it is 5 squared plus 1 squared. And then we take the square root. So if you want to find the sine of this angle, we have opposite over hypotenuse, 1 over the square root of 26. There. So in the process of figuring out an integral that has an upper limit of arctangent of a number, in that process, you're probably going to end up having to figure out the sine of the arctangent of that number. That is no big deal. You set up your triangle as we did in precalculus, and voila. You can still end up with nice exact answers. So this is an additional note I wanted to make. So that is notes. So this is note 1, Roman number 1, Roman number lowercase 2. Make sure when you are figuring out your rho So there's more stuff going on here. And probably a lot of the problems are going to have 0, but not necessarily. Not necessarily. But anyway, but that's not what I want to point out. Whatever your upper limit, don't confuse that with the projection. Oftentimes when we are working on problems with spherical coordinates, the projections are going to be nice circles. So for instance, back to the cone. Yeah. So you project the cone and you're going to end up with a nice circle. Don't confuse the radius, excuse me, of the circle with the radius corresponding to rho, or the distance, the maximum distance that rho can take, because that's going to give you the wrong answer. So in the example we finished in this video, this was 1, but this was the square root of 2. Had I given a sphere that was smaller with a radius of 1, for instance, so have we be given x squared plus y squared plus z squared equals 1, and z equals the square root of x squared plus y squared, then watch out, because then there's the sphere, this sphere, it's a unit sphere, and then when we intersect with a cone, assuming we have this cone, then when we drop this down here, we're going to end up with a circle, but the circle is going to be a smaller circle than the unit circle. I have to think about what it would be. It would be 1 over the square root of 2, that and that, if we had a 45-degree angle. Otherwise, you got to use some kind of arctangent. So watch out. The radius is 1 if we are working on, no, not even in, the distance, the farthest distance for rho would be, yes, 1 in this case. But if you were using cylindrical coordinates, then you have to, and you were using r, then r would go from 0 to 1 over the square root of 2. So there's a lot of details to keep track of. Just make sure you're careful. My grandma used to say, if you want to get there on time, go slowly. And what she meant by that is, be careful, because otherwise you have to do things all over again. It's kind of similar to measure twice, cut once kind of thing, because otherwise you have to do the work twice. All right, with this, we're going to stop this video.